Today we're going to look at a practice problem in power, and in this case we're going to be looking at a problem in which we're going to utilize the definition of power, where power can be defined as being equal to a force multiplied by a velocity. Looking at this problem, what we're going to be looking at is, in the problem we're told what the output power is. We're given a definition of the drag force as a function of several other values which are given within the problem statement itself. We're given that the drag coefficient is 0.29, that the frontal area is 5.95 square feet. We're also told that the density of air is 0.002326 slug per cubic foot. So what we want to do now is we want to begin looking at the aspect that we're going to try and determine what the theoretical top speed of this vehicle, where in this case we're looking at a Mazda RX-7. And we're assuming that the only thing that it needs to overcome is that of wind resistance. So if we look at this definition, power is given to us as being 146 horsepower. Now that we can actually know, we can convert to foot-pounds per second by multiplying by the 550 conversion unit, where we have foot-pounds per second, and that's per horsepower. That will now be equal to our foot drag force multiplied by our velocity. The interesting part about this now is the aspect that, well, the drag force itself is given to us as being 1/2 density multiplied by the velocity squared. And so what I'm going to do is I'm going to take this velocity squared and I'm going to actually move that to the end. So I'm going to put the drag coefficient on the area, and then I'm going to put the velocity squared at the end, and I'm going to multiply it with this additional velocity to obtain the aspect that I have velocity cubed. So FD multiplied by velocity is equal to this overall expression. As we begin to manipulate this now, what we find is we have 146 multiplied by the 550 gives us 80,300. That's in foot-pound per second, and that is going to be equal to 1/2 multiplied by our 0.002326 slug per foot cubed. That's going to be multiplied with our drag coefficient, which is given as 0.29, and our area, which is given as being 5.95 foot squared, multiplied by our velocity cubed. If we divide through by the 1/2, the 0.00232, the 0.29, and the 5.95, what we find is we get a value that is approximately equal to 4.001 times 10 to the 7th. That is equivalent to our velocity cubed. Now, as you could find as you work your way through this, you'll find that the units come in as being feet cubed per second cubed as you work through it. If we take the cube root of both sides, we find that we get 342 feet per second, which, if we check that in a conversion to miles per hour, multiplying by the 3,600 seconds in 1 hour and dividing by the 5,280 feet that are in 1 mile, we find that we get a value of 233.1 miles per hour. Now, the one thing that we need to, or that you should take into consideration, is the aspect that while this is the theoretically found value, we do want to take into consideration, is this realistic? And one thing that we can observe is the fact that obtaining 233 miles per hour is highly unlikely, and therefore there are obviously other things that we have not taken into consideration that are causing this car to not be able to completely convert its power to this kind of velocity. There must be more than just wind resistance slowing it down. But hopefully this problem helps you with a little more understanding of how power can be found from a force multiplied by a velocity.